Hi, welcome to video 12.1a, vector valued functions. Okay, so the title of the chapter is vector valued functions, the title of the section is vector valued functions, and I want to start by just, because it ties together. From 10.2 we learned parametric equations, x is f of t, y equals g of t. Remember when we graphed the plane curve, it had a direction as t increases, and sometimes it's just going to keep on happening. Sometimes restrictions are on x and y based on what f of t and g of t are equal to. So the definition of a vector valued function. So first of all, they will be capital letters, the names of vector valued functions. They will have the one-headed arrow over them, and they will be a function of t. And it'll be f of t times the unit vector I plus g of t times the unit vector j. Another way of writing it is in component form, which is just f of t, g of t. Okay, so you can think of it really as a set of parametric equations in effect. So, for example, if they give you the vector valued function r of t equals f of t plus g of t equals f of t I plus g of t j, r of 1, let's pretend that f of 1, oh, here we go. So I'm just making this up. Oh, no, here we go. X is equal to 3t and y is equal to t squared. Okay, so in other words, it would be 3ti plus t squared j right here. 3ti plus t squared j, or you could write it in component form. So for example, you could figure out r of 1 by simply replacing the t by 1. So you'd get f of t would be 3 times 1, g of t would be 1 squared, so that would give you in component form the vector 3, 1. If you plugged in t equals 2, you'd get the vector 6, 4. Now, this is going to be the terminal point here, of course. The point 3, 1 is the terminal point of the vector 3, 1, and the point 6, 4. And when we graph them, and this is the interesting thing, the graph of a vector valued function is the curve resulting from connecting the terminal points of all of the vectors. So you'll have this vector, we just found these two vectors, so we have the vector here 3, 1, the vector here 6, 4. The graph of the vector valued function is you joining up the terminal points only of all of the different vectors that you will find. Okay, so it's the collection of terminal points, and it will have a direction. The domain of a vector valued function is going to be the domain of f of t intersection with the domain of g of t. So as an example, is if you have r of t equals ln of ti plus square root of 1 minus tj, the domain of that vector valued function will be the intersection of the domain of ln of t. Of course, t has to be greater than 0. You can't take the log of a negative. And then intersection with the domain of the square root of 1 minus t. Well, of course, you can't. There's no imaginary numbers, so your radicand has to be greater than or equal to 0, and that means t has to be less than or equal to 1. So you have all values of t greater than 0 and less than or equal to 1, which means the following: interval from 0 to 1, including the 1. And that would be your domain. The other interesting thing about the domain of the function, it is in terms of t, no longer in terms of x. Okay, so it's not x as an element of. Keep in mind our vector valued functions are a function of t. Okay, this is a little interesting. If they give you a rectangular equation and they want you to write it in vector valued function form, well, all you need to do is simply just let x equals t, and then you're going to have y equals, and then you replace these x's by t's. It's the easiest way to do it. Now, of course, I could write it as a, this is kind of like in parametric form. This is more in vector valued function form. The limit of a vector valued function, if r of t equals f of t I plus g of t j, then the limit as t approaches a of r of t is the limit as t approaches a of f of t I plus the limit as t approaches a of g of t j. So it's only the f of t and the g of t that have a function of t. There's no t's in your unit vectors, so it's very simple to do. Definition of continuity of a vector valued function. A vector valued function R of t is continuous at the point given by t equals a. If, now this is the way your book says it, but of course, in order for a two-sided limit to exist, you'll notice there's no plus or minus here. That means the two one-sided limits would have to exist, and that's the famous trilogy from last year. All right, and I forgot to open the textbook to this, so let me pause. Okay, welcome back. So, you'll notice this is the exercises for 12.1. The domain, of course. Now, I do need to point out that they think you've done 3D. So you have a choice here. Anytime you see anything with K's in it, like, for example, number 7 is fine, but then we haven't done cross product. We have done dot product, but not cross product. But you can either ignore the part with the K on it and just pretend it only has I's and J's, or you can go ahead and deal with the third part. Okay, keep in mind if you do decide to ignore the K part, your answers will be different than at the back of the book. So if you wanted to do it the way the book does it and actually use the third dimension for the domain of these vector valued functions, you'd have to take the domain of the component of the coefficient of I, intersection with the domain of the coefficient of J, and then intersection as well with the domain of the intersection of the coefficient of K. And that way you'll get the answer in the back of the book. Numbers 9 through 12 says evaluate, if possible, the vector valued function at each given value of t. So we're going to look at number 10. R of t equals cos ti plus 2 sine tj, and then they're asking you to find r of 0, r of pi over 4, etc., etc., etc. So if we go back to our notes, number 10 is cosine ti plus 2 sine tj. R of 0 will be cosine of 0, which is 1. 2 sine of 0 is 2 times 0, which is 0. R of pi over 4, the cosine of pi over 4 is root 2 over 2. And this one will become 2 times root 2 over 2, which will just leave you with root 2. For theta minus pi, you're going to replace t by theta minus pi in both cases. And then what they're going to do is actually expand that. The cosine of a minus b equals cos a cos b plus sine a sine b. Same thing here, 2 times. The sine of alpha minus beta is the sine of alpha cosine of beta minus the cosine of alpha sine of beta. When you simplify all of this, of course, the cosine of pi is -1, so this will give negative cos. The sine of pi is 0, so this term here will just be 0. Then you have 2 times, again, the cosine of pi is -1 times sine theta, so you have -2 sine theta, and then, of course, again, what will happen is the sine of pi, what happened? Right, the sine of pi is 0, so this part just becomes 0. Okay, just kind of going back, here's number 6. They're asking you to find the domain. Okay, no. Oh, you have to find R of t first. Let's go back and look at that. So number 6, right, you have to actually find f of t minus g of t. And then, because they gave you f of t and g of t, but they're asking for the domain of r of t. So, in number 6, they told you f of t was ln ti plus 5tj minus, and then they told you g of t was I plus 4tj. So, I'm going to take, I'm going to write it in component form. It's just easier because you don't have to deal with the i's and the j's. So, I have ln t 5t minus 1 4t. And I'm just going to take the x component minus the x component, which will give me ln t minus 1, and then y component minus y component, which will give me t. So the domain of the vector valued function is the domain of the x component intersection with the domain of the y component. The domain of t is all real numbers, but the domain of ln of t, of course, you cannot take the ln of a negative or 0. Excuse me. So the intersection of the two is t is greater than 0. So t is an element of 0 to infinity. Notice it's t, not x. Number 14 They're simply asking you to find the magnitude of r of t. So number 14, r of t is sine 3t cos 3t. The magnitude of that, remember, is the square root of the square of the x component plus the square of the y component. The beauty is, of course, sine squared anything plus cos squared of that same thing is 1, and the square root of 1 is 1. Looking at number 20, right down here, it says find the dot product of r of t and u of t. Is the result a vector valued function? So looking at number 20, which is r of t is 3 cos t, 2 sine t, and u of t is 4 sine t negative 6 cos t. The question is, what is the dot product of r of t and u of t? So if you remember from dot product, all we have to do is multiply the x components and add to that the product of the y components. In this particular case, it turns out that the answer is 0. And of course, being a dot product, you should expect your answer to be a scalar, i.e. a constant. Okay, in numbers 27 through 42, it says sketch the curve represented by the vector valued function and give the orientation of the curve. Basically, this is the same as parametric. I mean, for example, for number 27, you can just look at this as the set of parametric equations. X equals t over 4 and y equals t minus 1. Okay, so try to eliminate, it's just like parametric, which means you'll try and eliminate the t and get a corresponding rectangular equation. Note the restrictions. If you can't eliminate t, you'll need to make a table for now, and on the ti, you will graph vector valued functions as parametric equations. And be careful of the t. Let it be a good negative 10 to 10 or negative 20 to 20 or whatever, because you might not be dealing with any trig. If you're dealing with trig, then 0 to 6.28 is usually fine. Okay, number 32 is asking you, I think that's in the same thing, yeah. So it's asking you to graph this function by hand. So basically that's the set of parametric equations, x equals 2 cos t, y equals 2 sine t. As you remember, we'll divide both sides by 2 and purposely square both sides. Sorry, I'm so tired. Square both sides and add them. So what happens is I end up with cos squared t plus sine squared t is 1. This gives me x squared over 4 plus y squared over 4. Multiply both sides by 4. You've got your circle. Now the restrictions do hold, everything's fine because cosine t would always be between negative 1 and 1. So 2 cosine t would be between negative 2 and 2, which means x is between negative 2 and 2, which is exactly what's happening. Okay, now graphing them on your calculator. Again, as we said, they're parametric, so you'll put your calculator in parametric mode. So for example, if you did this one, 3t plus 1, t squared plus sine t. Now remember, it automatically comes up as t is between 0 and 6.28, which is fine for this part of this y of t as far as the sign goes, but that's not going to work for us. Why would, if we had, like, for example, y equals 3x plus 1, why would you limit x to be between 0 and 6? So if you were to graph it, you'll only get this portion of it. You need to know to make that window a heck of a lot bigger. So if you make it negative 20 to 20, you'll get the rest of the graph.